Multicast addresses. Multicast addressing is supported by IPv4 and IPv6. An IP multicast address, also called group or group address, identifies a group of host interfaces rather than a single one. So, a multicast address identifies a group rather than a single host. Generally speaking, the group could span the entire internet if you're trying to send uh, a signal to the internet. The portion of the network that a single group cover is known as the group scope. So a single group, or the portion that it covers, is called the group scope. Common scopes include node local, same computer, link local, same subnet, site local, applicable to some site, global, entire internet, and administrative. Administrative scope addresses may be used in an area of the network that has been manually configured into routers. Administrative scope addresses may be used in an area of the network that has been manually configured into routers. So this type of scope addresses can be used in an area of a network that can be manually configured into routers. So a site administrator may configure routers as admin scope boundaries. So for this router that covers this network, it could configure that to be an admin scope boundaries, meaning that multicast traffic of the associated group is not forwarded past the router. So that what we mean with admin scope boundaries, it is not because like in OS you can only be a privileged user if you're an administrator. Note that the site local and administrative scopes are available for use only with multicast addressing. So this site local, which is applicable to some site or site specific network, it's not a subnet like link local, and the administrative scope are only available with multicast addressing. Under software control, the protocol stack in each internet host is able to join or leave a multicast group. Again, under software control, the protocol stack in each internet host is able to join or leave a multicast group. When a host sends something to a group, it creates a diagram using one of its own unicast IP addresses as the source address and a multicast IP address as the destination. So to be able to control who join or leave this multi-grass group, you need a software control uh, for each of this host in the network. When a host sends something to a group, it creates a datagram using one of its own unicast or IP addresses as the source address and a multicast IP address as the destination. All hosts in scope that have joined the group should receive any datagrams sent to the group. So, all hosts in scope that have joined the group should receive any datagrams sent to the group. Mhm. So let's say you have this link local scope and it joined a group site local, so any datagram sent to that group will be received by all the subnet. The sender is not generally aware of the host receiving the datagram unless they explicitly reply. Indeed, the sender does not even know in general how many hosts are receiving its datagrams. The original multicast service model described so far has become known as any source multicast. So those that include multiple scopes are known as any source multicast or ASM, but there's another model. In this model, any sender may send to any group. A receiver joins the group by specifying only the group address. So any sender could join this, for example, specified group, and a receiver will joins the group by specifying only the group address. For the receiver to receive datagram sent by this sender, it can join the group by specifying the group address. A newer approach called source-specific multicast or SSM uses only a single sender per group. So in this case, when joining group, uh, when joining a group, a host specify the address of a channel. Which comprises both a group address and a source IP address. SSM was developed to avoid some of the complexities in deploying the ESM model. Although neither form of multicast is widely available throughout the internet, it seems that SSM is now the more likely candidate for adoption. Details of how local IP multicast operates are given in Chapter 9. So the SSM is more simple because it has a single sender per group. So when joining a group, a host specifies the address of a channel, which comprises both a group address and a source IP address. So that's the sender, basically, for you to be able to join that group. So instead of just the So basically, instead of just the group address needed when joining, you also need, it's not called a group address, it is called now a channel, which you need a group address and the source IP address or the sender for that group, because it has a single sender per group. So these are more simple than just specifying a group address and then joining to that group, because those could become big. IPv4 multicast addresses. For IPv4, the class D space 224.0.0.0 to 239.255.255.255 has been reserved for supporting multicast. With 28 bits free, this provides for the possibility of 228 equals to 268,435,456 host groups. Each host group is an IP address. So since the class D are provided by this multicast address, it is reserved for providing this multicast addresses. So for the allocation before CIDI, we actually have this 268 million host groups that can provide this multicast. So this address space is divided into major sections based on the way they are allocated and handled with respect to routing. Those major sections are presented in table 2.9. So here, local network control not forwarded, inter-network control forwarded normally. The blocks of addresses up to 224.255.255.255 are allocated for the exclusive use of certain application, protocol, or organizations. So up to this reserve 224.255 here. So before ad hoc block, it is exclusive allocated for the exclusive use of certain application protocols or organizations. The local network control block, which is here, is limited to the local network of the sender. Datagrams sent to those addresses are never forwarded by multicast routers. So datagrams sent to that are never forwarded. It is only limited to the local network of the sender. Again, we have sender and groups when it comes to multicast. So the all host group 224.0.0.1 is one group in this block. So it's being sent by the sender to entirely to its own local network, which is kinda in SSM, the sender and the group block. So the interface control block is similar to the network control range, but is intended for controlled traffic that needs to be routed off the local link. So it is the same. It is controlled by sender and it's limited to the local network, but it is kind of like the outside controller for best effort delivery, which is intended to control traffic that needs to be routed off the link. An example from this block is the network time protocol multicast group. So NTP is one of this example of this. So the first ad hoc block was constructed to hold addresses that did not fall into either the local or inter-network control blocks. So this kind of like the evolution, because some addresses or multicast addresses did not fall in either local or inter-network control blocks. They created this ad hoc block. Most of the allocation in this range are for commercial services, some of which do not or never will require global address allocations. They may eventually be returned in favor of GLOB2 addressing. So they may actually return these addresses, or the global provider allocator may return this in favor of GLOB2 addressing, which is this we're gonna discuss later. The SDP or SAP block contains addresses used by applications such as the Session Directory Tool or SDR that send multicast session announcement using the Session Announcement Protocol or SAP. Originally a component of SAP, the newer Session Description Protocol SDP is now used not only with IP multicast but also with other mechanisms to describe multimedia sessions. So, a component of SAP, which is SDP, is now actually used not just for IP multicast but also with other mechanism to describe multimedia session. But if your app needs to support multicast session announcement, you may need to implement this protocol, IP protocol. The other major address blocks were created somewhat later in the evolution of IP multicast. The SSM block, which we discussed earlier, the one that has single sender per each group, uh, is used by applications employing SSM in combination with their own unicast source IP address in forming SSM channels as described previously. So this, if you want like a combination of unicast and multicast, you need to use this SSM. Now, the GLOP block, in the GLOP block, multicast addresses are based on autonomous system number of the host, on which the application allocating the address resides. In the GLOP block, multicast addresses are based on the autonomous system number of the host, on which the application allocating the address resides. So there's an AS number for application allocating the address or this IP address, and that's where these GLOP or multicast address are based. AS numbers are used by internet-wide routing protocols among ISPs in order to aggregate routes and apply routing policies. So for example, you have an application that allocates an address. This recent evolution that applies multicast address are actually being saved or used by internet-wide routing protocols, because it is used to automatically assign multicast address among ISPs. Um, in order to aggregate routes and apply routing policies. So this how they aggregate, the ISPs aggregates it and apply routing policies through these AS numbers. Each such AS has a unique AS number. Originally, AS numbers were 16 bits, but have now been extended to 32 bits. GLOP addresses are generated by placing a 16-bit AS number in the second and third bytes of the IPv4 multicast addresses, leaving room for 1 byte to represent the possible multicast addresses up to 256 addresses. So these GLOP addresses are generated placing a 16-bit AS number in the second and third byte. So remember, the second is from 8 to 24 bit of the IPv4 multicast address. Remember, it's 32 bits, leaving room for 1 byte or 8 bits to represent the possible multicast address, which is the 256 address. Thus, it is possible to map back and forth between 16-bit AS number and the GLOP multicast address range associated with an AS number. So this is how the ISPs automatically aggregate routes in this and apply routing policies. Although this computation is simple, several online calculators have been developed to do it too. The most recent of the IPv4 multicast address allocation mechanisms associates a number of multicast addresses with an IPv4 unicast address prefix. So here, unicast prefix based IPv4 multicast addresses. That's the most recent IPv4 multicast allocation mechanism. This is called unicast prefix based multicast addressing, or UBM, and is described in RFC 6034. It is based on a similar structure developed earlier for IPv4 that we discussed in section 2, for IPv6 that we discussed in section 2.5.4, which we used to convert IPv6 to IPv4. So the UBM, or the unicast prefix base multicast, the UBM IPv4 address range is 234.0.0.0 through 234.255.255.255. A unicast address allocation with a /24 or shorter prefix may make use of UBM addresses. So it's from 234.00 through 234.255, and then it's those where that prefix resides. A unicast address allocation with a /24 or shorter prefix So again, a unicast address allocation with a /24 or shorter prefix may make use of UBM addresses. So the reason why it is like IPv4 to IPv6 is because any unicast address allocation with the /24 or shorter prefix may make use of UBM addresses. So it can convert to that UBM from unicast to multicast. Allocation with fewer 25 or longer prefix must use some other mechanism. UBM addresses are constructed as a concatenation of the 234/28 prefix, the allocated unicast prefix, and the multicast group ID, which is here 234 8 bits unicast prefix. So this is up to 24. This is how you convert that unicast to multicast, and a group ID up to 16 bits. The IPv4 UBM address format for unicast address allocation of /24 or shorter, associated multicast address are allocated based on concatenation of the prefix 234/8. So any unicast address allocation of /24 or shorter for unicast are concatenated with 234/8. So you concatenate it to assigned unicast prefix and the multicast group ID. So allocations with shorter unicast prefix therefore contain more unicast and multicast addresses. To determine the set of UBM addresses associated with the unicast allocation, the allocated prefix is simply prefended with the 234/8 prefix. So for you to know the UBM multicast associated with this unicast address, you just need to prefend this 234/8 prefix. For example, the unicast IPv for prefix 192.0.2.0/24 has a single associated UBM address, 234.192.0.2. It's also possible to determine the owner of a multicast address by simply left shifting the multicast address by 8-bit position. So to know the owner, we just need to left shift this by 8-bit because this 234/8 again is the first byte or the first position of this in the in its address. 8 plus 24 plus 16 that is equals to 24 plus 8 is 32 and sorry it's still a 32 bits, right? So up to 24 doesn't mean it's 24, up to 16 bits doesn't mean it's 16. So the first few bits is 8 bits, the unicast prefix is up to 24, therefore that will determine the group ID because it can only contain 32 bits. So we know that multicast address range 234.128.32.0/24 is allocated to UC Berkeley, for example, because the corresponding unicast IPv4 address space 128.32.0.0/16, the left shifted version of 234.128.32.0, is owned by UC Berkeley. UBM addresses may offer advantages over other types of multicast address allocation. This is the reason why it is the most recent as well, the UBM. For example, they do not carry the 16-bit restriction for AS numbers used by GLOP addressing. In addition, they are allocated as a consequence of already existing unicast address space allocation. So again, in addition, they are allocated as a consequence of already existing unicast address space allocations. So the reason is it is already allocated using this unicast address space allocation, meaning they are able to you're able to convert it to UBM. So it is convenient. Thus, sites wishing to use multicast address already know which addresses they can use without further coordination with the the IANA. So because it's already provided to them if they have that, if they convert it. So finally, UBM addresses are allocated at a finer granularity than GLOP addresses, which correspond to AS number allocations. So again, finally, UBM addresses are allocated at a finer granularity than GLOP addresses, which corresponds to AS number allocations. So it is a finer granularity than GLOP addresses because GLOP needs or corresponds to the AS number allocation rather than unicast. In today's internet, a single AS number may be associated with multiple sites. So this single AS provided by GLOP could be from multiple sites, frustrating the simple mapping between address and owner supported by UBM. So instead of being able to convert that to the actual unicast host, you need to determine which site it is converted because a single AS could be in multiple sites. The administratively scope address block, which is in the last part, can be used to limit the distribution of a multicast traffic to a particular collection of routers and hosts. So this address can be used to limit the distribution of traffic to a certain routers and hosts that you want to be sent that datagram for multicast to. These are the multicast analogs of private unicast IP addresses. Such addresses should not be used for distributing multicast into the internet. As most of them are blocked at enterprise boundaries. So these addresses should not be used for distributing multicast addresses into the internet because they are blocked at enterprise boundaries. Large sites sometimes subdivide administratively scope multicast addresses to cover specific useful scope like work group, division, and geographical area. So if you have a large site like Amazon or AWS, you could subdivide this administratively scope multicast to cover useful scope, such as dividing it to a work group, geographical area, etc. This is also how you divide the access into multiple areas through AWS or through your ISPs. So Anycast address is a unicast IPv4 or IPv6 addresses. Is a Anycast address is a unicast, so it's a unicast. It's not multicast. It could be IPv4 or IPv6 that identifies a different host depending on where in the network it is used. So these others are used to identify a different host depending on where in the network it is used. This is accomplished by configuring internet routers to advertise the same unicast routes from multiple locations in the internet. So Anycast, it's a kind of like magic because it identifies a different host depending on where the network it will be used. So it provides a different host depending on the network. So this is accomplished by configuring internet routers to advertise the same unicast routes from multiple locations in the internet. So you can provide or advertise whatever suit to that network. Thus, an Anycast address refers not to a single host in the internet, but to the most appropriate or closest single host that is responding to the Anycast address. So sorry, let me refine the definition. Basically, this Anycast address is a unicast address that is not referred to a single sender connected to a group, just like the SSM, but rather it's different depending on where network you are located, depending on what near uh, uh, single host that is responding to the Anycast address. For example, you're in Bulacan and the Anycast address responding is this host B, and you're in, for example, in Pampanga, and the Anycast address responding is host C. It really depends where you're located. Anycast addressing is used most frequently for finding a computer that provides a common service. For example, a datagram sent to any cast address could be used to find a DNS server. So it is used to find a DNS server. That's the most common use to be able to translate it fast. A 624 gateway that encapsulates IPv6 traffic in IPv4 tunnels. So it can be also used for gateway that encapsulate IPv6 traffic in IPv4 tunnel, just like the uh, concept we mentioned in the previous video on how we encapsulate IPv6 in IPv4 and then make it IPv6 again to if the network doesn't have an IPv6 path or IPs for multicast routing. Allocation. The authorities are generally organizations that allocate address space to various owners, usually ISPs or other smaller authorities. Authorities are most often involved in allocating portions of the global unicast address space. So usually they allocate a unicast rather than multicast or anycast. But other types of addresses like multicast and special use are also sometimes allocated. So these authorities, such as your internet provider, usually allocate unicast. So unicast, for unicast IPv4 and IPv6 address space, the IANA delegate much of its allocation authority to a few regional internet registries. The IIRs coordinate with each other through an organization formed in 2003 called the Number Resource Organization. Note, in addition, that as of early 2011, all the remaining unicast IPv4 address space held by IANA for allocation had been handed over to these IRs. So here are an example. For Asia, we're only concerned with apnic.net. So these are the regional that allocates to our ISPs. So this they allocate address space to smaller registries operating in countries such as Australia and Singapore, and to large ISPs. ISPs in turn provide address space to their customers and themselves. When users sign up for internet service, they're ordinarily provided a typically small fraction or range of their ISP's address space in the form of an address prefix. These address ranges are owned and managed by the customer ISPs and are called provider aggregatable address because they consist of one or more prefixes that can be aggregated with other prefixes the ISP owns. So what do we mean by ISP? Provider aggregable ISPs, right? So what do we mean by provider aggregatable addresses? Because they consist of one or more prefixes that can be aggregated with other prefixes the ISP owns. Example, ISP receives 203.0.113.0/20 from RIR. ISP splits it into 203.0.113.0/24 for customer A, 203.0.114.0/25 for customer B, 203.0.114.128/25 for internal routers, and so on. They are still part of the original /20, just smaller sub-prefixes. So it's still part of the /20, but smaller sub-prefixes. So what we mean by in the form of an address prefix, or when users sign up for internet service, they are ordinarily provided a typically small fraction of the range of their ISP's address space in the form of address prefix. So that's what we mean by that. In global routing, the ISPs often are advertised as only the /20 via BGP, so all traffic destined to those customers is aggregated through a single route. So any route directing to customer A or B are being aggregated into a single route. So that's what we mean by provider aggregatable addresses. This is why they're called provider aggregatable addresses. The provider ISP can keep the global routing table small while still handing out smaller ranges internally. So for AWS example, AWS is essentially a very large ISP. It holds a huge address blocks from RIRs. RIR gives AWS something big like 3.0.0.0/8. They have multiple large allocations. AWS subdivides internally. For BPC in a customer account, 3.5.10.0/24. Another region, 3.6.0.0/16, etc. But AWS doesn't change the CIDR in the sense of inventing their own new prefix. They allocate subnets from their own CIDR blocks and route them internally and externally. So they still use the CIDR, or the modern way, to allocate addresses, unicast addresses, but they allocate subnet from their own CIDR blocks, and Mind you, like IANA provided them a large block. So if they run out of block in a region, they may allocate from a different IR block they own. But again, it's their own registered space. There's a crucial reason ISPs and AWS don't just make up new IP ranges because of the global BGP routing tables. Global BGP routing tables depend on prefixes being owned and registered properly. If they were to use random ranges or alter allocations arbitrarily, routing on the internet would break. They can only subdivide smaller prefix, form bigger one, advertise the aggregate bigger prefix, so they will advertise the bigger prefix to provide to the customer, but subdivide it to a smaller prefix from bigger one. In special cases, advertise more specific prefixes if needed for traffic engineering. But they can't invent new prefixes they don't own because it's not provided to them by IANA. So such addresses are also sometimes called non-portable addresses. Switching providers typically require customer to change the IP prefixes on all computers and routers they have that are attached to the internet. So all of the IP addresses you have that for your computers and routers and iPad, laptop will be changed if you change the provider, an often unpleasant separation called renumbering. So if you want to save it or to not change your IP address, therefore you need to contact the RIR or regional, but it will be costly. An alternative type of address space is called provider independent IP. Provider independent address space. Addresses allocated from PI space are allocated to the user directly and may be used with any ISP. However, because such addresses are owned by the customer, they're not numerically adjacent to the ISP's own addresses. So because they're not numerically adjacent, just like in aggregation of routing table, they will need to save like more routing tables, just like in the heap structure of the tree that we discussed earlier, the adjacent one where it provides the adjacent IP, which save a lot of routing table entries, and therefore are not aggregatable. So as an ISP being asked to provide routing for a customer's PI addresses may require additional payment for service or simply not agree to support such a configuration. In some sense, an ISP that agrees to provide routing for a customer's PI addresses is taking on an extra cost relative to other customers by having to increase the size of its routing tables. On the other hand, many sites prefer to use PI addresses and might be willing to pay extra for them because it helps to avoid the need to renumber when switching ISPs, avoiding what has become known as provider lock. It is possible to use the Internet WUIS service to determine how address space has been allocated. For example, we can form a query for information about the IPv4 address 72.1.140.203 by accessing the corresponding URL http wuis.rin.net/rest/ip/72.1.140.203 text. So here's an example. Here we see that the address 72.1.140.203 is really part of the network called SpecSys part-1, which has been allocated the address range 72.1.140.192/27. Furthermore, we can see that spec C5 part 1's address range is a portion of the PA address space called net 72-1 128-1. We can formulate a query for information about this network by visiting the URL wuis.rin.net/rest/net/net 72-1-128-01 text. So we can look at a different type of result using one of the RIRs. For example, if we search for information regarding the IPv4 address 193.5.93.80 using the web query interface at http uh, www.ripe.net/whois, we obtain the following. So here we can see the address 193.5.93.80 is a portion of the 193.5.88.0/21. Block allocated to WIPO. Note that the status of this block is assigned PI, meaning that this particular block of addresses is of the provider independent variety. The reference to our PSL indicates that the database records are in the routing policy separation language used by ISPs to express their routing policies. Such information allows network operators to configure routers to help minimize internet routing instabilities. Multicast. An IPv4 and IPv6 multicast address group addresses can be described based on their scope. In IPv4 and IPv6 multicast addresses, group addresses can be described based on their scope. The way they are determined statically, dynamically by agreement, or algorithmically, and whether they are used for ASM or SSM, which mostly the SSM today, which is a single sender and with a per group for multicast. So again, in IPv4 and IPv6 multicast address, group addresses can be described based on their scope. The way they are determined statically, dynamically by agreement, or algorithmically. So these multicast addresses are actually determined by their scope, right? We have link local, host only, site. We also have global, and also it is determined by how they are allocated, whether it's statically, dynamically by agreement, or algorithmically, and whether they use ASM or SSM. This is the properties that define multicast addresses. Guidelines have been constructed for allocation of these groups for IPv4 groups, for RFC 5771 for IPv4, RFC 3307 for IPv6, and the overall architecture is detailed in RFC 6308. The groups that are not of global scope, like administratively scope addresses and IPv6 link scope multicast addresses, can be reused in various parts of the internet. So again, the groups that are not of a global scope, like administratively scope address and IPv6 link scope multicast addresses, can be reused in various parts of the internet and are either configured by a network administrator out of an administratively scoped address block or selected automatically by end host. Globally scoped addresses that are statically allocated are generally fixed and may be hard-coded into applications. So for statically allocated multicast address, it's generally fixed or global scope address that are statically allocated or generally fixed and may be hard-coded into applications. So this type of address space is limited, especially in IPv4. So such addresses are really intended for uses applicable to any internet site. Algorithmically determined globally scope address can be created based on AS numbers, as in GLOP or an associated unicast prefix allocation. So for algorithm allocated for multicast, it could be from GLOP or the unicast conversion or the UBM as well. So note that SSM can use globally scope address from the SSM block. Administratively scope addresses or unicast prefix based IPv6 address where the prefix is effectively 0. As we can see from the relatively large number of protocols and the complexity of various multicast addresses formats, multicast address management is a formidable issue, not to mention global multicast routing. From a typical user's point of view, multicasting is used rarely and may be of limited concern. From a programmer's point of view, it may be worthwhile to support multicast in application designs. And some insight has been provided in how to do so. For network administration faced with implementing multicast, some interaction with the service provider is likely necessary. In addition, some guidelines for multicast address allocation have been developed by vendors. So link layer introduction. In chapter 1, we saw that the purpose of link layer in the TCP or IP protocol suite is to send and receive IP datagrams for the IP modules. So it talked with the IP module. And we also discussed in the previous video how it is called frame instead of segment for transport layer and instead of packet. It is also used to carry a few other protocols that help support IP, such as ARP. So this link layer, aside from supporting these IP modules or from the TCP or IP or datagram for this IP module, it also used to support protocols such as ARP, right? So these are where the ARP is located. TCP or IP supports many different link layers depending on the type of networking hardware being used. Wired LANs such as Ethernet, metropolitan area network such as so it also support TCP or IP stock that we have discussed also support other type of networking hardware like wired LANs for Ethernet. So this is what we usually think when we think of link layer. Metropolitan area networks such as cable TV and DSL connection available through service provider. So cable TV could be supported by this TCP or IP. That's why a cable TV could be connected to the internet nowadays. And wired voice networks such as telephone lines with modems. And also telephone lines that's why it's usually connected to a router, right? As well as the more recent wireless network such as the Wi-Fi. So the Wi-Fi is and the Ethernet is the most common way people see this being used, right? Or this is what their first intuition when they heard this. In this chapter, we shall look at some of the details involved in using the Ethernet and Wi-Fi link layers. So because this is the most useful, how the point-to-point protocol PPP is used, and how link layer protocols can be carried inside other link or higher protocols, a technique known as tunneling. So again, in this chapter, we shall look at some of the details involved in using Ethernet and Wi-Fi, link layers, how the point-to-point protocol is used, and how link layer protocols such as ARP and different other protocols supported in this layer can be carried inside link or higher layer protocols. So will also discuss how those can be accessed in higher level protocols aside from just link, a technique called known as tunneling. Covering the details of every link technology available today would require a separate text, so instead we focus on some of the most commonly used link layer protocols and how they are used by TCP or IP. Most link layer technologies have an associated protocol format that describe how the corresponding PDUs must be constructed in order to be carried by the network hardware. So they have the protocol format which describe or provide us a guide how the corresponding frame must be constructed in order to be carried by the network hardware. So depending on the hardware we support, whether it's landline, cable TV, wireless, Ethernet, these guidelines will define or help us to create this link layer to be able to carry by that hardware. So frame formats usually support a variable length frame size ranging from a few bytes. So again, byte is 8 bits to a few kilobytes. So it's a variable depending on the hardware it supports. The upper bound of the range is called the maximum transmission unit or MTU, a characteristic of the link layer that we shall encounter numerous times in the remaining chapters. Oh my god. Some network technologies such as modems and serial lines do not impose their own maximum frame size, so they can be configured by the user. So again, the upper bound of the range is called the maximum transmission unit. So the range or the upper bound size is the called maximum transmission unit, a characteristic of the link layer that we shall encounter numerous times in this chapter. Some network technologies such as modems and serial lines do not impose their own maximum frame size, so they can be configured by the user. So a serial line such as those for DSL or for landline and some modems do not enforce this upper bound or frame size, so they can be configured by the user. Ethernet and IEEE 88 Ethernet and IEEE 802 LAN and MAN standards. So the term Ethernet generally refers to a set of standards first published in 1980 and revised in 1982 by Digital Equipment Corp, Intel Corp, and Xerox Corp. The first common form of Ethernet is now sometimes called 10 millibytes Ethernet or shared Ethernet, and it was adopted with minor changes by the IEEE as the standard number 802.3. So when we see Ethernet, we're actually referring to a set of standards for guidelines to be communicated to talk to this network hardware. So the first common form of internet is called 10 millibytes per internet, which supports obviously 10 millibytes or shared ethernet, and it was adopted with minor changes by the IEEE as the number 802.3, and it was established by IEEE in their research paper and allow it to be used around the world. So that IEEE provides the guideline in their research to be able to implement that in other parts of the world. So here we have a shared Ethernet segment, or what we call LAN. So this is what we call IEEE 802 point 3. So these are LAN that can support LAN and MAN standards. As you can see, we have different stations. A basic shared Ethernet network consists of one or more stations, workstations, supercomputers attached to a shared cable segment. Link layer PDUs frames can be sent from one station to one or more others when the medium is determined to be free. So the frame from link layer can be sent from one station to another when this medium or internet, let's describe this communication, is free. If multiple stations send at the same time, possibly because of signal propagation delays, a collision occurs. So this is where collision, if multiple stations send at the same time. Kind of like in a concurrency problem. So collisions can be detected, and they cause sending stations to wait a random amount of time before retrying. So thankfully these Ethernet standards define it as it will wait algorithmically a random amount of time before retrying, usually double the amount of time as it encounters collision. So this common scheme is called carrier sense multiple access with collision detection. So this is actually what we call CSMD. So that again is a part of the guideline of this Ethernet or 802.3. At present, switches are commonly used, providing each Ethernet station with the ability to send and receive data simultaneously, called full duplex Ethernet. So for this type of LAN, switches are commonly used. It provides each Ethernet station with the ability to send and receive data simultaneously, called full duplex Ethernet. So the full duplex Ethernet guides us that it has a switch, but it also allows multiple stations to send concurrently. Although half duplex one direction at a time operation is still supported even by 1000 millibytes Ethernet or 100 base T, it is rarely used relative to full duplex Ethernet. We shall discuss how switches process PDUs in more detail later. So we will discuss how it is, the guidelines on how to actually process that PDU by the Ethernet by the switch later. One of the most popular technologies used to access the internet today is wireless networking. So one of the Most popular technologies used to access the internet today. So this LAN has just been, connected. Imagine this just become bigger using a wireless networking. So the most common for wireless local area, the most common for wireless local area networks, WLANs, being an IEEE standard known as wireless fidelity or Wi-Fi, and sometimes called wireless Ethernet. So it's still an Ethernet. It's just provide a bigger network, or 802.11. So earlier, the Ethernet for LAN with the internet is 802.3. Now a Wi-Fi is actually 802.11. Although this standard is distinct from the 802 wired Ethernet standards. So these guidelines are distinct because it's wireless from the 802 wired Ethernet standards. The frame format and general interface are largely borrowed from 802.3. So again, the guidelines are largely borrowed from that, simple LAN and Ethernet, and all part of this set of IEEE 802 LAN standards. Thus, most of the capabilities used by TCP or IP for Ethernet networks are also used for Wi-Fi networks. So all of the thus because of that, most of the capability that TCP provide for Ethernet are also used now for Wi-Fi. So yeah, if the TCP provides some capability to the internet before, it can also be supported with this wireless Ethernet. First, however, it is useful to get a bigger picture of all of the IEEE 802 standards that are relevant for setting up home and enterprise networks. So the IEEE 802 LAN or MAN standards. So before we get into that one Wi-Fi networks, we need to be familiar with the standards that are relevant for setting up whether the Ethernet LAN home networks or an enterprise network or company network. So the IEEE 802 LAN and MAN standards. The original Ethernet frame format and operation were described by industry agreement mentioned earlier. This format was known as the original Ethernet frame or the guideline from LAN are originally described by industry agreement. So this format was known as the DICS format or Ethernet 2 format. So this is the first standard that was created. This format was known as DICS format or Ethernet 2 format. This type of Ethernet network with slight modification was later standardized by the IEEE as a form of CSMA/CD network. So this is actually where this format is where the collusion avoidance or CSMA/CD network format came from. So this type of Ethernet network with just slight the modification was later standardized by the IEEE as a form of CSMA/CD network called 802.3. So this is where the 802.3 came from. In the world of IEEE standards, standard with the prefix 802 define the operations of LANs and MANs. So again, LANs are local area network, and MAN are I forgot what man or yeah, metropolitan area networks such as the cable TV and DSL connection connect. So for 802, that those define the operations of the LAN and the MAN. So these are the example. LAN and MAN IEE standards, multiple registration protocol (MRP), relevant as DCIP 2000, and MAC security or MACsec, link aggregation formerly 802.3 AD, MAC bridges, traffic classes, priority slash cost, virtual bridge LANs slash correction to MRP, multiple spanning tree protocol MSTP, rapid spanning tree protocol RSTP, port based network protocol 802. So these are all the 802 point something protocol. Just look at it, guys. I'm not gonna read everything. The most popular 802 standards today include 802.3, essentially Ethernet, and 802.11 1 slash or Wi-Fi. These standards have evolved over time and have changed names as freestanding amendments, like 802.11g, are ultimately incorporated in revised standards. Other than specific types of LAN networks defined by the 802.3, 802.11, and 802.16 standards, there are some related standards that apply across all of the IEEE standard LAN technologies. Common to all of the three of this is 802.2 standard that defines the logical link control frame header common among many of the 802 networks frame formats. I think we'll just have to continue with this. So let's stop here, the Ethernet frame format. In IEEE terminology, other than specific type of LAN networks defined by the 802.3, 802.11, and 802.6 standards, there are some related standards that apply across all of the IEEE standard LAN technologies. Common to all three of these is the 802.2 standard that define logical link layer frame header common among many of the 802 network frame formats. In IEEE terminology, LLCs and MACs are sublayer of the link layer, where LLC, mostly frame format, is generally common to each type of networks, and the MAC layer may be somewhat different. While the original Ethernet made use of CSMA/CD, for example, WLANs often make use of CSMA/CA. Is a collision avoidance. So, yeah, I'm so toasted now. The frame format is remained essentially the same until fairly recently. So, to get an understanding of the details of the format and how it has evolved, we now turn our focus to this detail. So the Ethernet frame format, we'll discuss that in the future videos.